When you hear the words artificial intelligence, what do you picture? Maybe it's a robot, or maybe it's Chat GPT. Maybe it's some giant computer somewhere. Or maybe you don't really know what to picture. I didn't either, because we hear words like AI and the cloud all the time, and they make this technology sound almost invisible. But while I've been investigating AI and the data centers being developed here in West Virginia, I realized there was a really basic question that I hadn't asked. Where is it? Physically, where is it? When you ask AI a question, when it creates an image, when a company trains one of these systems, somewhere physical machines have to do that work. So, where are those machines? What do they look like? And why does something we think of as software suddenly have us talking about electricity, cooling systems, substations, transmission lines, land, and even water? That's when I realized I had been looking at this backwards. When I'm trying to understand something this big, I've learned not to listen only to what people say. I look at what they're doing. Then I look for what keeps happening. Because behavior creates patterns, and patterns leave clues. Look at what companies are actually building. Because AI may feel invisible, but it isn't. AI has to happen somewhere, and that's where we are starting. Let's follow the machine. Okay, let's break this down and make this as simple as possible. AI needs computers, real ones. And inside those very real computers are processors doing enormous amounts of mathematical work. You've probably heard of the term GPU, and if you haven't, don't worry about remembering it. A GPU is a type of processor that is very good at doing many calculations at once. They became heavily associated with things like computer graphics and gaming. But it turns out that kind of computing is also extremely useful for AI. There are other specialized AI processors too. Google, for example, developed processors called TPUs. But I'm not going to bury you in a bunch of letters and technical language. GPU, TPU, whatever comes next, here's what actually matters for our investigation. AI requires physical computing hardware. And for the biggest AI systems, we're not talking about one computer sitting on somebody's desk. We're talking about large numbers of powerful processors working together. Those computers go into servers. Those servers get stacked into something called a rack. Think of a rack like a tall metal bookshelf, except instead of books, it's packed with all kinds of computing equipment. Now, here's where this starts getting interesting. Because the moment we start putting more and more computing power into those racks, the machines begin creating other problems we have to solve. And the first one is electricity. So let's follow the power. Years ago, a conventional computer rack might use somewhere around 5 to 15 kilowatts. Now look at what's being built for AI. There are systems out there with all kinds of names and fancy numbers behind them, so I'm just going to give a very general example. So, NVIDIA has a system that can put roughly 125 to 135 kilowatts of operating power into a single rack. One rack. And I'm not giving you that number because I expect you to remember 125 or 135 kilowatts. I'm giving it to you because of what is going to happen next. When you concentrate that much computing power into one place, getting enough electricity to those computers becomes part of the engineering problem. And that's our first clue. The computers aren't simply sitting inside a building using electricity. At these densities, the electrical system has to be designed around them. Now, multiply those racks. One rack becomes 10, and 10 rows become a room filled with rows of servers. Rows fill rooms, rooms fill buildings, and buildings can turn into giant campuses. And as the computing grows, you start seeing more of the physical infrastructure that's required to support it. Transformers, switchgear, substations, electrical distribution equipment, backup systems, and depending on the project, potentially new or upgraded transmission infrastructure or power generation. So the computers aren't just filling the building, they're starting to change and shape our infrastructure. That's our first big clue, because something else happens to nearly all that electricity once it reaches the computers. It becomes heat. Computers get hot, and more computing power that you pack into a small space, the more heat that you have concentrated in that small space. Think about the radiator in your car. If your engine gets hot, liquid absorbs some of that heat and carries it somewhere else so the engine can keep operating. We're increasingly seeing that same basic idea applied directly to high density AI hardware. Traditional data centers have relied heavily on air cooling. Fans move air across the equipment. Cool air goes in and then the hot air comes out. That still works for plenty of computing equipment, but at the highest AI rack densities, moving enough heat with that air becomes increasingly difficult. That's why direct to chip liquid cooling has become an important part of these high density AI systems. Liquid moves close to the processors. It absorbs that heat. Then it carries that heat away. But here's something I didn't really think about before I started digging into this. Moving the heat away from the chip doesn't make the heat disappear, it just moves the problem. Now you just have hot liquid, and you still have to get that heat out of the liquid and out of the building, and ultimately into the surrounding environment. That's where equipment such as pumps, heat exchangers, chillers, cooling towers, or other heat rejection systems can come into the picture, depending on how the facility is designed. And depending on the cooling system, that can also bring us to water. But we're going to investigate water separately because there's an important distinction here. Not every data center uses the same cooling system, and not every cooling system uses water in the same way. So I'm not going to give you one giant number and pretend that it applies to every facility. That's a question we're going to investigate on its own. But for now, notice what happened. We followed the computer, it led us to electricity. And we followed the electricity, which led us to the heat. Now we're following the heat and it's leading us to the cooling. And we're still not finished, because thousands of powerful computers aren't very useful if they cannot communicate with one another. Imagine giving 10,000 people different pieces of the same enormous math problem. Everybody starts working. Great. But they constantly have to exchange information with one another. If communication is slow, people start sitting around and waiting. That's essentially one of the problems engineers have to solve inside large AI computing systems. Thousands of processors may need to exchange enormous amounts of information very quickly. Think of processors like cars. If you put 100,000 of them on a two-lane road, it doesn't really matter how fast any of those cars can go, you've just created a traffic jam. You see, inside these systems, the network is just like a highway. So, alongside all those processors, you need extremely fast networking equipment and fiber connections moving information between them. Then there's storage. You see, AI systems also need to access huge amounts of information, and having lots of storage just isn't enough. The computers need to retrieve information quickly. Imagine having access to the biggest library in the world, which, by the way, would be absolutely amazing. But every time you ask for a book, it takes the librarian 3 hours to bring it to you. Technically, you do have access to everything, but you're going to spend an awful lot of time waiting. So it's the same basic problem. You don't want extremely expensive computing equipment just sitting idle waiting for information to flow. So now we've added fast storage to our machine: computing, networking, storage, and something has to coordinate all of it. That's where software comes in. Software helps manage workloads across enormous numbers of components. Where should this job run? Is there something overheating? Did something fail? Is part of the network overloaded? Does work need to move somewhere else? Think of it like air traffic control, but for the data center. There may be an enormous amount happening all at once, but something has to coordinate it. And eventually, something is going to break. So let's talk about following the failure because this is another part that I hadn't really considered. You see, when you're dealing with enormously expensive computing systems, you don't design everything around the assumption that nothing will ever fail. You design around the reality that eventually something is going to fail. Equipment fails, power can be interrupted, components will need maintenance. So facilities use backup and redundant systems. You may have batteries that bridge power interruptions, backup generators, or other emergency power systems. You'll have duplicate equipment. You may hear engineers use terms like N1 redundancy. It sounds complicated, but the basic idea isn't. If you absolutely need four of something to keep operating, you might install five. You still have four. That's redundancy. And now look at what has happened. We started with computers, but the more important those computers have become, the more physical systems have to surround them in order to keep operating. All right, so let's kind of like zoom out and try to picture the whole thing. We started with a processor. We put those processors into servers, stacking the servers into racks. Then we're putting rows of racks into rooms, and now we're putting those rooms inside of large buildings and potentially putting multiple of those buildings together on one big campus. But those buildings don't stand alone. They do need electrical infrastructure, cooling infrastructure, networking, fiber, storage, backup systems, security, fire protection, road access, and of course, land. Some fully loaded computing racks can weigh thousands of pounds, so even parts of the building itself may have to be engineered around the equipment inside. And companies increasingly use prefabricated components to speed construction. Think of it as like industrial Lego. Piece by piece, you start to see why the picture I had in my head was wrong. I used to hear the word data center and picture like some Area 51 giant warehouse full of computers. And that's not completely wrong, but for the largest AI facilities, it's nowhere near the whole picture. A better way for me to understand it is this: it's an industrial computing complex, part supercomputer, part electrical system, part cooling plant, part communications network, and it's all working together to produce computing power. And that's when all the clues we have been following start to become a pattern. Behavior leaves clues. So let's forget all the social media hype, all the news, and all the advertising for a minute, okay? Forget predictions about AI and forget the promises that AI is going to change everything. And then also forget the AI is the end of the world, it's doomsday, run, get a bomb shelter. Those are arguments about what might happen. Instead, let's look at the behavior that we can actually observe right now. Companies are investing in increasingly powerful computing systems. Those systems require electricity. That electricity creates heat. That heat has to be removed. The machines have to communicate. Information has to be stored and moved. And systems have to be built around keeping all of it operating. All right, let's cover some facts. Fact number one: high density AI computing requires physical computing equipment along with substantial electrical, cooling, and networking infrastructure. Fact number two: as computing density increases, engineers have to solve increasingly demanding power and heat removal problems. Fact number three: some current high density AI rack scale systems are already operating above 100 kilowatts per rack. Now, here's where we have to separate what we know from what we infer. And infer basically means what does the evidence suggest? Here's what it suggests. When companies commit enormous amounts of money, equipment, infrastructure to increasing AI computing capacity, their behavior suggests that they expect substantial demand for that computing capacity. That does not prove every prediction they're making about AI will come true. It doesn't prove every data center being proposed will get built. And it doesn't tell us whether all of this investment will even ultimately pay off. Those remain open questions, but the infrastructure itself tells us something. AI isn't floating around somewhere in the cloud. AI has a physical address. It has buildings. It has machines. It needs electricity. It produces heat. And all of that has to physically exist somewhere. That's the clue I almost missed when I started this investigation. Because from where most of us encounter AI, it just looks like software, the computer screen, or the phone in front of us. But if you follow the machines, eventually you find the physical systems underneath of it. All right, let's talk about why this matters. And this is the part that I really hope you understand. You don't have to use ChatGPT. You don't have to understand GPUs. You don't have to care which AI company wins. You don't have to know anything about computer science. You don't have to know anything about smartphones, any of it. Because once AI requires physical infrastructure, it enters the same physical world that the rest of us live in. It needs land, electricity, cooling, construction, infrastructure. And depending on the facility and cooling design, potentially significant water resources. Those things don't exist in some imaginary digital world. They exist in our communities. And that means the AI story eventually becomes a story about things that don't sound like technology at all. Power plants, electric bills, transmission lines, water systems, land use, taxes, jobs, local government, and who gets to make decisions about all of it. AI has to happen somewhere, and somewhere belongs to somebody. That's where this investigation gets more interesting. When I started looking into AI, I thought I was investigating technology, but look at what we actually followed. A chip led us to a rack. The rack led us to electricity. Electricity led us to heat. Heat led to cooling. And thousands of machines working together led us to networking, storage, and all the systems required to keep them running. Follow it far enough, and you end up with something much bigger than a room full of computers. You end up with industrial scale infrastructure. That's the pattern. And it leaves us with a clue that's going to matter for everything we investigate from here forward. AI has to happen somewhere. And here in West Virginia, somewhere can be right here at home. We've already found data center development coming in our state. Now we understand something we didn't at the beginning of this investigation. These facilities don't just need land and computers. They need power, a lot of it. And that takes us to our next question. Where is all of that electricity supposed to come from? And maybe more importantly, who's going to pay for it? Because that's where this stops being just a story about AI. It becomes a story about power plants, utilities, infrastructure, and potentially our communities and our electric bills. That's what I'm investigating next. So if you want to follow this investigation as we uncover it, subscribe and come with me. And before you go, I want to know something. Before this episode, when somebody said AI data center, what did you picture? A warehouse, a bunch of computers, something floating around in the cloud? Or did you have no idea at all? You have to tell me in the comments because that's exactly why we're doing this investigation. Behavior creates patterns. Patterns leave clues. And the truth is rarely sitting right on the surface. Sometimes you have to follow the clues, and that's exactly what we're going to keep doing.